Solubility equilibrium. This is pages 565 to 567 in your textbook. You're definitely going to want to check that out as an additional resource and additional review. Solubility. Solubility is the amount of material that will dissolve in a given amount of solvent. So we've looked at solubility last chapter, and we've looked at how things dissolve and which things dissolve, but now we're going to actually quantify it. We're not just going to say something precipitates or not precipitates. We're going to put some numbers along with that. If we're looking at this reaction with calcium fluoride is dissolving. So we're adding calcium fluoride to the water. It's a solid. And what happens? Well, it dissolves. And by dissolving, it breaks apart into two pieces. It breaks into calcium ions and fluoride ions. Which process dominates? Well, initially we just have water and we add the calcium fluoride. So initially this forward reaction dominates because I don't have any of these guys in solution. So many will break apart. But eventually, what is attained? We'll attain equilibrium. When we attain equilibrium, we'll have a fixed amount of calcium fluoride, the extra that hasn't dissolved, and we'll have our ions. But know that equilibrium is never static, and that some of these might come back together to form calcium fluoride, and when it does, some of these will break apart to make calcium and fluorine ions. So we've attained equilibrium. We're going to write the equilibrium expression. We're going to call it KSP, and the SP stands for solubility product. Our equation is this calcium fluoride, which yields calcium ions plus fluorine ions. So our KSP is just like we've learned with any other K expression, is that it's equal to products, which is Ca plus 2, and then F minus, and that's going to be squared because of this 2 here. But for any KSP problem, there is no denominator. Remember, when we write a K expression, we can only include things that are aqueous or gaseous because their concentrations can change. We cannot include solids or liquids, okay? And since CaF2, and for every KSP problem, your reactant here is going to be a solid, they're not going to be included, so we're not going to have a denominator. So it says write the KSP for, and we have a couple of different choices. So for barium hydroxide, and the easiest thing to do is to go ahead and write the reaction. We always need a reaction. So we're going to split this into Ba plus 2, aqueous, plus 2 OH minus aqueous. We'll go ahead and write the expression as KSP is equal to Ba plus 2 OH minus squared. Another one to try, lead carbonate. We'll split that apart into, again, Pb plus 2 aqueous plus CO3 minus 2 aqueous. And we'll write this as KSP is equal to Pb plus 2 CO3 minus 2. And now we have this compound. So we have silver, which is plus 1, aqueous, plus CrO4. We know this is a minus 2 because we know that Ag is plus 1 and there's 2 of them. Aqueous, and KSP equal to Ag plus 1, CrO4 minus 2. Ooh, and I have 2 Ags, I almost forgot, and so I need to put that 2 there, and then I also need to put that 2 there. My last one, calcium phosphate, becomes Ca plus 2, and let's not forget that I have 3 of them, plus 2 PO4 minus 3s, aqueous, aqueous. And again, aqueous is important in this case because we want to let people know that we can put them in a KSP expression, that we know that it's something that we can include. So we'll have Ca plus 2 to the third, PO4 minus 3 squared. If we add more solid, let's say we put solid in, we let it dissolve. What happens if we add more solid? If we already have solid on the bottom. Good sound effects there. More solid does equal more surface area. We would have more surface area for things to dissolve. Does the equilibrium shift? Not at all. And we learned this when we, last unit, when we went ahead and dissolved the potassium nitrate and the sodium chloride into water. We stirred and stirred and stirred and stirred until it was saturated. And it didn't matter if we would add more salt or more potassium nitrate. More of it would not dissolve. So it says, explain then, how does grinding up the solid or stirring affect solubility? And this we learned earlier. Well, grinding up the solid gives us more surface area, and stirring allows it to mix faster. So it speeds the attainment of equilibrium. We get to equilibrium faster with smaller pieces and with stirring, but we don't change the amount dissolved. And that we've already covered, but that's just a good review. Some differences. The solubility product, it is, I don't know why it says some differences. It says the equilibrium constant for the dissolving of a slightly soluble salt. So typically we're looking at things that don't dissolve very much, because we know in equilibrium, even though if we said things precipitate, there's always going to be some of those ions in solution, just not very many. So we consider things to be a precipitate or insoluble, but they really do dissolve a tiny, tiny, tiny bit. And solubility is an equilibrium position depending on the situation of the solution. And so we're going to see how we can go ahead and apply this with calculations. So we're going to learn to calculate the KSP from solubility data. We have a problem here with silver sulfide. It has a solubility of 3.4 times 10 to the 17th molar at 25 degrees Celsius. Again, we give this temperature even though we're not really going to use it. And so it says to calculate the KSP for Ag2S. Well, first we have to write the reaction. Ag2S solid becomes 2Ag plus 1 aqueous plus S minus 2 aqueous. We're going to go ahead and write our KSP expression. So KSP is equal to Ag plus 1 squared times S minus 2. We know that Ag2S has this solubility. So we know that S also has this solubility because S is in a 1-to-1 ratio with Ag2S. There's a 1 here, so we know if we know the solubility of this, we know the solubility of this. But how many more Ags dissolve? Well, 2 more dissolve. So in order to solve for the KSP, and this is going to be true every time we're going to follow this, we need to do 2 times whatever concentration we're given for something that has a 2 here for a coefficient. So 3.4 times 10 to the minus 17. And this one, we can just go ahead and write in 3.4 times 10 to the minus 17. I'm going to go ahead and solve this out. And so I would go ahead and multiply by 2 first. Oh, I'm sorry, and I need to square this. Oh my goodness, I cannot forget to square this. This square stays with it. So I'm going to double it because of this 2, but then I'm also going to square it. And then this is times 3.4 times 10 to the minus 17. And then I encourage you to pause and make sure that you can calculate this, but square this number, multiply it by 3.4, and we end up with 1.57 times 10 to the negative 49th. Now notice that's a tiny KSP because not very much dissolves. I mean, look at this. We know that this is a precipitate, and look at what our molarity is when the most of it dissolves. I mean, look at that tiny molarity. And then look at this tiny KSP, which tells us that it's something that's not very soluble. Let's try it again, just to make sure we got it. So now we're going to look at bismuth sulfide. And so again, we're going to write our reaction. Bi2S3 solid, and I'll try not to forget any superscripts this time, becomes 2Vi plus 3 aqueous plus 3S minus 2 aqueous. I'm going to go ahead and write my KSP, which is equal to Vi plus 3 squared and S minus 2 to the third. Now I'm going to solve for my KSP by plugging in the values that I have. And so I have 1 times 10 to the 15th. Well, I have to multiply my first one by 2. So if I raise something to 2, I multiply it by 2. Minus 15. And then what do you think I want to multiply this sulfide by? Well, I'm raising it to 3, so I want to multiply it by 3. And then also cube it. Oh, and I forgot that squared again. I'm so sorry. I need to make sure that I carry down my exponents for both of those. KSP, let's see, I went ahead and forgot a superscript, is equal to 2.0 times 10 to the minus 15th squared times 3.0 times 10 to the minus 15th cubed. I'm going to go ahead, I'm going to ask you to try to solve this on your own. And you're going to get 1.08 times 10 to the negative 73. Very, very, very little bit will dissolve. Okay, in fact, we consider both of these things to be precipitates. Now, what if I'm given the solubility and I need to solve for the KSP? Well, the KSP value for copper 2 iodate is 1.4 times 10 to the 7th. So that's the KSP value. Calculate its solubility. We're always going to start with our equation. So we have CuIO3 2, which is a solid, which will break into Cu plus 2 aqueous plus 2IO3 minus 1 aqueous. My KSP is equal to Cu plus 2 and then IO3 minus 1 squared. Well, I'm working backwards. I know the KSP, so I need to solve for my concentrations. So I'm going to work backwards from what I did before. If I'm going to go ahead and put in 1.4 times 10 to the minus 7, I'm going to go ahead and put in X for Cu. But since before I had to multiply this number by 2 of whatever my solubility was, I'm going to go ahead and make this 2X. So anytime it's squared, this is going to be 2X. Anytime it's 1, this is going to be 1X. If it was 3, this would be 3X. I'm going to go ahead and solve. One thing that people really forget to do is they forget to distribute this 2 to here. And so what I end up, I have X times 4X squared. Biggest mistake is to write 2X squared and not 4X squared. I have 1.4 times 10 to the minus 7 is equal to 4x cubed. And then I'm going to divide each side by 4 so that I get x cubed is equal to 3.5 times 10 to the minus 8. And therefore my x is equal to, and if you need to learn how to do a cube root, you can raise something to the 1/3 power. That will give you the cube root. Or you can see me, or you can see your math teacher to learn how to plug that into your calculator. But you want to make sure that you can take the cube root. So pause it. Okay, and then check that you got 0.00327 molar. And that would be our solubility. Let's try it one more time with a little bit trickier problem. What is the KSP for barium chloride if 0.059 grams dissolves in 1 liter of solution? Well, now we're solving for the KSP, but instead of being so kind and giving you the molarity, I gave you grams. And so that just, it's the same thing, but it's going to add an extra step. We need to figure out our